Hi guys, in this video we're going to go over momentum quickly and then we're going to try to answer these two questions about trying to figure out what is the average force in a bat and what was the total kinetic energy after. So things to know about momentum. Momentum, we give the letter P and it's equal to the mass times the velocity. So its unit always is kilograms meters per second because it's a mass in kilograms times the velocity in meters per second. An equation that comes up quite often in momentum is an equation that says force is equal to the rate in change in momentum. So force is equal to the rate in change in momentum. And this equation shows us why cars always have that large crumple zone at the front of them. So cars, even electric cars, right? So normally cars you think have that big section in front of them because of where the engine is. Even electric cars still have the big section in front of them even though the battery is normally underneath the car. The reason we keep that big section in the front is because let's say you're driving along and something happens that you hit a wall, okay? You want to make sure that the force on you is as low as possible so you don't break any of your bones, right? So this is why it's called the crumple zone. So what happens is when you hit the wall, it's going to take this crumple zone, it's going to take time for that to crash in on itself. And what happens is because we're increasing the time then, you can see for the same change in momentum, so because the car might have been going at 50 meters per second, the car might have had a mass of, I don't know, like 200 kilograms. Okay, so it's going to have the same change in momentum because it got momentum before, and let's say it comes to rest completely at zero momentum. For the same change in momentum, if we have that crumple zone there, we can increase the time over which that change in momentum happens, we can see the value of force there is going to go down. So that's why you're going to feel a less force on your face or less force in your body. So we keep that crumple zone there. Same reason why when you get your packages from Amazon is that why they're wrapped in that bubble wrap, because if they are to drop, it takes time for that bubble wrap to compress, increasing the time, so decreasing the force on whatever the breakable objects are inside that package. Other ways you might see this is you might see a graph. We've got force plotted against time. Okay, and it might be something like a triangle shape, and you get asked to find out what is the speed of an object after, if it starts at rest. So let's say it starts at rest, we can figure out if I've got a force graph, force times time gives me the change in momentum. So force times time, that's the area under the graph. So we can see there is that the area under that graph is going to give us what the change in momentum is. So if I know it started at rest, and I know what the mass is, so the first speed, initial speed is 0, and I know the mass is, let's say it's still got a mass of 200 kilograms, I can use the area under that graph to figure out what the final speed is going to be. Okay, key things about these graphs, remember what you normally do if it's a triangle, you just do half the base times the height, or sometimes what they like to do with these questions is give you boxes. So they might give you like kind of looking like a curve shape, and then they'll give you those really large boxes. So all you want to do here is that you always will find the area of one box, so it's base times the height, and then you're just going to count the number of boxes. For this one, I would do 1, 2, 3, there's this plus this would give me 4, this is about 5, this plus this would give me 6. So you find the area of one box and you multiply by 6 to find the area under the graph. So again, you do that when they give you those really large boxes. That's when they give you the large boxes, try to make it obvious that you count the boxes. Okay, so this one we got a cricket ball moving at 0.16 kilograms, moving at 30 meters per second, makes contact for 50 milliseconds. The ball moves off in the opposite direction at 27 meters per second. So we want to find what the force is. So I know to calculate the force, we have to do the change in momentum over time. So I'm going to draw a picture. So I've got my cricket bat. I've got a ball that's coming in with a speed of 30 meters per second. And normally I like to take things going towards the left as negative. So let's say it's going in at negative 30 meters per second. That's its direction. We know that it's got a mass of 0.16 kilograms. It makes contact with the bat for 50 milliseconds, or 50 times 10 to the negative 3, and then it goes off in the opposite direction at 27. So I'm going to keep the right as positive 27 meters per second. So to calculate the force, what we're going to do here is the change in momentum. So the change in momentum is its final minus initial. So the final is my 27 times by 0.16. And we're taking away the initial. The initial is, the mass is 0.16. times by the velocity was my negative 30. And then we're dividing by our time, and our time is our 50 times 10 to the power of negative 3. Okay, hopefully you see here what ends up, this becomes a positive number because a negative times by negative gives me a positive. So in your calculator, when you do this, what you should have done is 27 multiplied by 0.16. So 27 multiplied 0.16, and then we're going to subtract a negative number, so a negative, negatives, positives. So I should end up adding 0.16 times by 30. And the top part there of our fraction is going to be 9.12. So force is equal to 9.12 divided by 50 times 10 to the negative 3. To give us a force of 182.4 newtons. So grand. Okay, next one says that I'm going to have an object here. It's moving at 12 meters per second to the right. So I've got some object that's moving at 12 meters per second towards the right. It's got a mass of 7,500 kilograms. It's going to collide with an object that's also moving to the right at 90 meters per second. I know it's also moving to the right because it gives the same number. So it's going to collide with some object that's moving at 19 meters per second, and it's got a mass of 2,500. So you can clearly see, because this one's going faster, eventually it's going to catch up, and that's why they end up colliding. I want to find the total kinetic energy after. So it says they're going to stick together. So I know because momentum is conserved, the momentum before must always equal the momentum after. So the total momentum before is going to be the mass times velocity. So 7,500 times the velocity, which is 12. We're going to add in its mass, which is my 2,500 times by 19. So momentum of the one object before plus the momentum of the second object before is equal to the momentum after. It says they stick together, so their combined mass is going to be 7,500 plus 2,500 times whatever speed they're moving at. So I can solve this for speed. So all we're doing here is 7,500 multiplied by 12. We're going to add on 2,500 multiplied by 19. And we divide that number by the combined mass, which is 7,500 plus 2,500 to get what our V is. And our V comes out there, our final speed comes out at 13.75 meters per second. So this question wants us to find what the total kinetic energy is after. So I know to find the kinetic energy, that equation is 1/2 of its mass times its speed squared. So what I'm going to do now is 1/2 of the mass, the combined mass, which is my 7,500 plus my 2,500, which clearly is going to be my 10,000, times my speed that I just calculated earlier, which is 13.75 squared. So when you do that in your calculator, so we're going to do 13.75 squared multiplied by 10,000 and divided by 2 gives us a kinetic energy after of 945,312.5 joules. Okay, so you can even calculate the total kinetic energy before. And if you do the total kinetic energy before here, it's not going to give the same number. So I do the total kinetic energy before, if I do the kinetic energy of this object, and I add it to the kinetic energy of this object, so my kinetic energy here is going to be 1/2, or 0.5, times by 7,500 times by 12 squared, which is going to give me 5,40000. And for this one, again, its kinetic energy is 0.5 times its mass, 2,500, times its speed, which is 19 squared. We get a number here of 4,51250. So the total kinetic energy before, if we add those to get 5,40000, we get a total kinetic energy before of 991250 joules. So we can see here the kinetic energy after is much less than the kinetic energy before. So here, this kinetic energy is not conserved, so we call it as an inelastic collision. So when kinetic energy is not conserved, it's an inelastic collision. If kinetic energy is conserved, it's an elastic collision.